All right. Okay, so today we are going to start on section 4.7. And that covers optimization. Which is mainly just the idea of minimizing or maximizing. Okay, so most of these are in story problem form. So if you're anything like me, didn't really look forward to story problems. But here are a few guidelines to hopefully help. It's where you're not just running at them, hoping something jumps out at you. It gives you kind of a playbook. Okay, so the first thing you want to do is you want to identify all of the quantities given to you. So identify all given quantities and equations. And in some cases, making a quick little sketch helps visualize it. So next, you want to write your primary equation. And that's for the quantity that's going to be minimized or maximized. Uh-oh. Okay. Now the third step is only if it's necessary. Okay. So you want to reduce the equation in step 2 to an equation of one variable. So you want to reduce the equation from step 2 to having one independent variable. To having one independent variable. Okay, so you don't want it written implicitly, you want it written explicitly as an equation of one variable. And sometimes this would involve a secondary equation. A secondary equation. Do, 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 do. Okay, so after that, you want to find your domain, or at least identify it. Sometimes it's needed, sometimes it's not, but it's always good to have. And if you want, you can do this first or next to last or whichever one. It's kind of flexible. Then from there, you want to determine the minimum and maximum values just using all the processes we've learned so far. So determine the minimum or maximum values. Using the techniques learned so far, or up to this point. And that could be the first or second derivative test. The chain rule, or whatever process that particular problem needs. All right. Oh, let's do. Okay. So let's say, for example, we know that the product of two positive numbers is 192. And the sum is a minimum. Okay, so you want to find the two numbers that satisfy the requirements. Okay, so by this one saying the sum is a minimum, they really just mean that out of all the numbers that you could multiply together to give you 192, if you add these two together, they'll give you the smallest sum. Okay, so let's look at the first step. We're going to identify what's given to us. Okay, so we have the product of two positive numbers is 192. So what's given is x times some number y equals 192. Okay, so they gave us the sum as a minimum, but they didn't give us really a value. So we can't say that was given to us because there's no value to it. But that sum as a minimum does give us our primary equation because that's what's being minimized, the sum. Okay, so we'll let the sum, we'll let that be some number we'll call S, is equal to x plus y. That's because the sum is being minimized. So that is our primary equation. Okay, so our third step is we have to take that primary equation, and in this case, it's a function of x and y. So we have to reduce that to either just a function of x or just a function of y. Okay, so we need one independent variable. Okay, and actually we have the secondary equation we can use to do that. So we know that since we know that x times y equals 192, we can divide both sides by x, and we can just have y is equal to 192 divided by x. That's our secondary equation. Okay, so that means that our primary equation, s is equal to x plus y, that becomes s is equal to x plus, and instead of y, we can make it 192 over x. Okay, so now we have a function with one independent variable. So we know x is the only independent variable. Okay, which brings us to our fourth step, just identifying the domain. Okay, well, they did tell us that's the product of two positive numbers. So really the only domain is that x is greater than 0 and y is greater than 0. In the fifth step, in this case, we want to find the minimum. Okay, so if we start off with our primary equation, s is equal to x plus 192 over x, right in one independent variable. Then we just find the derivative of s with respect to x. Well, the derivative of x is just 1, so that's 1. And the derivative of 192 over x is negative 192 over x squared. And I'll just put that as a little side note here. And that's the derivative with respect to x. And we're going to rewrite that as 192 times x to the negative 1 power. And using the power rule, that negative comes down, so that's negative 192 times x to the negative 1 minus 1, which gives us negative 192 times x to the negative 2 power, or negative 192 over x squared. Okay. So we know to find our minimum or maximum, we have to find where the derivative is equal to 0. The derivative of s with respect to x equals 0 when 1 minus 192 over x squared is equal to 0. So if we add 192 over x squared to both sides and then multiply both sides by x squared, we end up with x squared is equal to 192. And if you plug it in, you get 192 over 192, so 1 minus 1 will equal 0, so that would be true. So we square root both sides. See that x is equal to plus or minus the square root of 192. Okay. But if we look at our domain, we know x has to be greater than 0, so we're not going to use the negative. So all we're going to use is the positive since that's the case. So x is equal to the square root of 192. Okay. But now we have to find the y value. And we can use our secondary equation for that one. Y is equal to 192 divided by x. Well, we know that x is equal to the square root of 192. So that's y is equal to, I'll kind of separate that a little bit. And that 192, we're just going to rewrite that as the square root of 192 squared, square root of 192. So if you multiply those two together, you just get 192 divided by x, which is the square root of 192. Okay, so these two cancel each other out. So we see that y is equal to the square root of 192. So these are our minimum sums. If you add those two together, they will give you the smallest sum out of every possible combination of numbers that could multiply to give you 192. All right. Any questions on that one? All right. Anyone still writing? All right, so let's say, for example, if we know that the perimeter of a rectangle, let's say rectangular room, just to have it as an actual application. So the perimeter of a rectangular room is 100 meters. So we're going to find the maximum area. Okay, so let's identify what was given to us. So if we draw our rectangular room, we know that these two parallel sides are equal length, so we'll call that some length x. And these two parallel sides are equal, so we will call that some length y. And we know that the perimeter is equal to 100 meters. So the perimeter, you're just counting the length of the edges and adding them up. So that means we know that if we get side x plus side x plus side y plus side y, add those together, we'll get 100. So that x plus x, we'll just write that as 2x, plus that y plus y, we'll write that as 2y, is equal to 100. Okay. So we know that's not our primary equation because we want to find the maximum of the area, and that's just the perimeter. So if anything, that's going to be our secondary equation. Okay, so that's our first step. Now the second step, that's where we find our primary equation. Okay. Well, since we're maximizing the area of a rectangular room, we're going to need the area of a rectangle. So we know that the area is equal to the length times the width. So if they said a circular room, we need the area of a circle. So in this case, our primary equation is just A is equal to X times Y, since that's our length times width. But once again, we have a function of X and Y, and we need one independent variable, not two. So one independent variable. Okay. So using our secondary, well, not really our secondary equation, but using this equation, we know that we can have 2x plus 2y equals 100. So if we subtract 2x from both sides, that gives us 2y is equal to 100 minus 2x. So if we divide each term by 2, those two cancel out. So we have y is equal to 100 divided by 2 is 50, minus these 2's cancel out, so it's just minus x. Okay, so we were able to take this and create our secondary equation. So now we take our primary equation, which is a is equal to x times y. So now we can replace that y. So we have a is equal to x times 50 minus x. So if we distribute that x, just to simplify it a little bit, we have a is equal to, and if you want, because now a is a function of just x, you can say a, or you can say a of x. Same exact thing, so it's up to you whether or not you want to actually do that, but you can. So that's x times 50, which is 50x, minus x times x, which is x squared. So we have our function of one variable. Okay, so for this one, again, this fourth step, a lot of times you can skip it. This one, the domain, we just know that since it's a rectangular room, x and y would have to be positive. So I guess it's one of those things where from a lot of problems you can skip it, but it never hurts. Okay, so now for our fifth step, we take our function is equal to 50x minus x squared, and we find our derivative so we can find our minimum or maximum. well, maximum in this case. You can say the derivative of a with respect to x, or you can say a prime of x. Again, completely up to you. Is equal to 50 times the derivative of x. So that's 50 times 1, which is 50, minus the derivative of x squared, which is 2x. So again, we know that our maximum or our minimum occurs at the point where your derivative is 0. So a prime of x equals 0 when 50 minus 2x is equal to 0. So if we add 2x to both sides, that gives us 50 is equal to 2x. So if we divide both sides by 2, we get 25 is equal to x, or x is equal to 25. And the good thing about your secondary equation is that you can get that value and just plug it in and solve for y. So we know that y equals 50 minus x. Since x is 25, we have y is equal to 50 minus 25, or y is equal to 25. Now, these are not always equal. I know the first two examples were both equal. That's not always the case. That's sometimes the case, but not always. So I don't want you to think every time it's going to be equal. So x equals y equals 25 provides the maximum area. Okay, so these first two being equal is just strictly coincidence. All right, any questions on that one? All right. So let's say, for example, if a farmer plans to fence in a rectangular recipient pasture adjacent to a river. Okay, so we know that the pasture must contain 180,000 square meters to have enough grass to feed the herd. Okay, so what dimensions would require the least amount of fencing. If no fence is needed along the river. Okay, so let's look at the first step. We want to identify what's given to us. Okay, well, it says that the pasture must contain 180,000 square meters in order to have enough grass. So if we draw a little sketch here, so let's say this is our rectangular pasture. But if this side is the river, there's no fence needed along the river. So we only need the fence along here and here and here. Okay, so we'll say that the width, we'll give that length of x. Or the length, you can call it the length or the width, doesn't matter since you're multiplying them. And the length is a length of y. And again, we don't need any along the fence, so we're good. And the area is just the amount of space inside of here. So we know that the area is equal to 180,000 square meters. Okay, so we know the area of this rectangular pasture is equal to the length times the width. Well, in this case, length times width is just x times y. Okay, well, we already know that the area is expected to be 180,000 square meters. So that gives us x times y has to equal 180,000. Okay, so we have our given, and we have what most likely will be used to produce our secondary equation. But first, we have to find our primary equation. Okay, so what if we let S represent the amount of fencing we would need? And we kind of separate these two. Well, instead of amount, I'll say length of fencing needed. Amount sounds a little too vague, so I'll say length of fencing needed. Okay, so if this is the case, then S would just equal y plus x plus y. Or you can say x plus 2y. Okay, so once again, we have two independent variables. And we only need one. Which brings us to our third step. Making that one independent variable. Bring that up a little bit. Okay. Well, we know x times y is 180,000. So if we divide both sides by x, that gives us y is equal to 180,000 divided by x, which gives us our secondary equation. So if we could just get that y, so since we know that s is equal to x plus 2y, we can just replace that y. So that gives us s is equal to x plus 2 times 180,000 divided by x. So if we go ahead and multiply 2 times 180,000, that gives us the length of fence needed is equal to x plus 360,000 divided by x. 360,000 divided by x. Okay, so now that we have our one independent variable, we just have to find the derivative of that to give us our minimum or maximum. And again, the fourth step, in this case, you could skip it because it just shows x is greater than 0, y is greater than 0. Like I said, some cases it's completely necessary, but in cases like this, it's kind of obvious, but it doesn't hurt. So our fifth step is now where we find the minimum. And that is where the derivative of s with respect to x is equal to 0. Okay, well, if we take our derivative of s with respect to x, That's equal to the derivative of x, which is just 1, minus the derivative of 360,000 times x to the negative 1 power. We bring down the negative 1, so that's negative 360,000. And that's to the power of negative 1 minus 1, so that's to the negative 2 power, which we could just put in our denominator. Okay, so we know the derivative of s with respect to x is equal to 0, when 1 minus 360,000 divided by x squared is equal to 0. And we'll finish it up on the next page. Okay, just write down where we left off. 1 minus 360,000 divided by x squared is equal to 0. So if we add 360,000 over x squared to both sides and multiply both sides by x squared, we get x squared is equal to 360,000. And of course, you plug it in, you get 1 minus 1, which is 0, so we know that's true. Move that one out of the way. So if we square root both sides, we have the square root of x squared, which is just x, is equal to plus or minus the square root of 360,000, which is 600. But since we know x has to be greater than 0, we know x is equal to 600 meters. So now we use this to solve for the length or width, whichever one you want to identify y as. Use to solve for y. Okay, so since we know that from our secondary equation, y is equal to 180,000 divided by x. So since x is 600, means that y is equal to 180,000 divided by 600, which means that y is equal to 300 meters. Okay, so those are your dimensions, but the total fencing needed which is our minimum. Remember, that sum was equal to x plus 2y. So that sum is equal to x, which is 600 meters, plus 2 times 300 meters. So that's 1,200 meters minimum. So that would be the minimum amount of fencing that you would have to still have 180,000 square meters? All right. Any questions on that one? All right. Go. So let's say, for example, if a car company charges its customers some unknown value we'll call P, number of dollars per day to rent a car, where we know that the price is somewhere between $45 and $200. So the number of cars rented per day can be modeled using the linear formula. The number of cars at that price is equal to 800 minus 4p. Bring that over a little bit. How much should the company charge each customer to maximize revenue? Okay, so let's look at the first step. What was given to us? We know that the number of cars at a particular price would be 800 minus 4 times P. Okay. And we also know that the range of the price, or you can say the domain, is between $45 and $200. So actually this is the fourth step, so we can kind of do that here. That's why I was saying it's flexible where you can do the fourth step. You don't have to do it as the fourth. But we can just put it right there with the given if it was given to us. Okay. So now we have to look for our primary equation. And we're looking to maximize revenue. So we know that our primary equation should involve the revenue. Can't maximize revenue if you don't have the equation for the revenue. So we have our primary equation. Okay. So we know, let me clean that arrow up a little bit, that the revenue in this case is just the number of cars rented times the price of the rental. I clean that up a little bit. Or you could just say R is equal to N times P. So again, we have two independent variables. We only need one. The third step, we have to create that one independent variable. Okay, so we know that our revenue is R equals N times P. But if we look at our given, we know that N is equal to 800 minus 4P. So instead of R is equal to N times P, we have R is equal to 800 minus 4P times P. So if we distribute that P, we know that our revenue is 800P minus 4P squared, or we could say the revenue is equal to negative 4P squared plus 800P. Where we have our one independent variable. Let me clean up that P a little bit. So we have our one independent variable. Actually, you don't have to write it again, just draw the arrow right there. And again, the fourth step was already done up there, so there's no need to do it again. our fifth step. We want to find the maximum value, or in this case, maximum revenue. Which means we have to find the rate of change of R with respect to the price. So the derivative of R, or derivative of the revenue with respect to the price, we need to find where that is equal to 0, because that'll give us our minimum and maximum. So we know that's equal to 0 when negative 4p squared. Actually, we have to find the derivative of negative 4p squared. The derivative with respect to p of negative 4p squared plus 800p is equal to 0. Okay, so the derivative of R with respect to p is equal to the derivative of negative 4p squared. So we bring down the 2, that's negative 8 times p to the power of 2 minus 1, which is just 1, plus the derivative of 800p is just 800. And we want to find where that is equal to 0. And I'll move this over. There we go. So negative 8p plus 800 equals 0. If we add 8p to both sides, it gives us 800 equals 8 times p, or 8 times p equals 800. So if we divide both sides by 8, that gives us a price that is $100. Remember, that is our critical point. And we'll finish this up on the next page. Okay. Now the thing about this one is that, remember, the price is between $45 and $200. So it's possible you can get the maximum revenue at $45, or you can get it at $200, or you can get it at the critical point of $100. So we have to plug all three of those values into our one independent variable equation to find out which is which. All right, so let's write that on the next page. So we have to find our 100, because that's our critical point. We have to find our 45. And R of 200. Okay, remember, those are still part of our domain. To see which provides the maximum revenue. Okay, now in most cases it's the critical point, but it is still possible to be the two endpoints of your domain. Okay, so the revenue when the price is $100. That's 800. Actually, let me write out the original revenue equation so we don't have to keep flipping back and forth. So, 800. Let me write it out in the factored form. It'd be a little easier to plug in. 800 minus 4p times p. So the revenue at $100 is 800 minus 4 times 100 times 100. Well, that gives us a revenue of $40,000. And I'll just kind of separate each one. Now the revenue at $45 is 800 minus 4 times 45 times 45. Well, that gives us a revenue of $27,900. And the revenue at $200 is equal to 800 minus 4 times 200 times 200. And that gives us a revenue of $0. So the maximum revenue is found at $100. So the price equals $100 maximizes revenue. All right, any questions on that one? Okay. So again, the steps aren't necessary. You can do it your own way if you like, but it's just very helpful to have a process in place and not just kind of going at each problem blindly, which is where a lot of story problems get intimidating because you don't know where to start. All right, any questions on that one? In there. All right. Okay. Now we're going to look at section 4.8, which covers L'Hopital's rule. And sometimes you look at it and it's spelled L'Hôpital's with an S, which I don't know why they have one spelling with an S and one without, where it looks like the hospital's rule, but it's always spelled without the S here, and then all of a sudden the S started popping up, so I have no clue which is the proper spelling, but it's one or the other. Okay, so what if we let some function f of x and g of x represent differentiable functions? Where we know that the derivative of g of x is not equal to 0. Okay. So if the limit of f of x divided by g of x as x approaches some value c equals an indeterminate form, and those indeterminate forms, there are a couple of them. It could be 0 over 0, or any combination of positive or negative infinity divided by positive or negative infinity. It could be positive infinity divided by negative infinity divided by positive infinity, any combination. And it equals that through direct substitution. Okay. Now, if that's the case, then we know that the limit of f of x divided by g of x as x approaches c is equal to the limit of the derivative of f of x divided by the derivative of g of x as x approaches c. Well, let's say, for example, if we wanted to find the limit as x approaches -1 of 2x squared minus 2 over x plus 1. And yes, there are easier ways to do this one, but we'll just use this example for L'Hôpital's rule. Okay. So if we take the limit of 2x squared minus 2 over x plus 1 as x approaches -1, we use direct substitution. That's the limit as x approaches -1 of 2 times -1 squared minus 2 divided by -1 plus 1. So actually, we don't need the limit once we use direct substitution. So that actually just gives us 0 divided by 0, which is one of the indeterminate forms. So once we have our indeterminate form, that's when we can use L'Hopital's rule. So all that means is that the limit as x approaches -1 of 2x squared minus 2 over x plus 1 is equal to the limit as x approaches -1 of the derivative of 2x squared minus 2 divided by the derivative of x plus 1. So we're not taking the derivative of the whole thing, because that would just be the quotient rule. We're taking the derivative of the numerator separate from the derivative of the denominator. So we have the limit as x approaches -1. The derivative of 2x squared minus 2 is just 4x. Divided by the derivative of x plus 1. The derivative of x is 1. The derivative of 1 is 0, so it's just 1. So we know the limit as x approaches -1 is just equal to, well, of 4x. I won't say is equal to 4x, but it's just 4 times x. So now we apply direct substitution again. And as long as you don't have another indeterminate form, you can just plug it right in. So that's just 4 times -1, which is -4. All right, any questions on that one? All right. So let's say if we wanted to find the limit of 3x squared minus 1 divided by 2x squared plus 1 as x approaches infinity. Okay, so if we see our limit as x approaches infinity of 3x squared minus 1 divided by 2x squared plus 1, we go to just our numerator, and you don't have to write this out, you can just apply it, but I'll write it out. 3x squared minus 1 as x approaches infinity divided by the limit of 2x squared plus 1. There we go. Well, if we plug in numbers that are bigger and bigger and bigger and bigger, this whole numerator just gets bigger and bigger and bigger and bigger. So that's just infinity over the same thing with the denominator. Cuff keeps grabbing the paper. So we end up with infinity over infinity, which is one of our indeterminate forms. So we can't apply L'Hopital's rule until we put it in the indeterminate form. So here we can use L'Hopital's rule. So we know that the limit of 3x squared minus 1 over 2x squared plus 1 as x approaches infinity is equal to the limit as x approaches infinity of the derivative of 3x squared minus 1 divided by the derivative of 2x squared plus 1. So it's equal to the limit as x approaches infinity. The derivative of 3x squared is 6x divided by the derivative of 2x squared plus 1 is 4x. Of course, the derivative of the minus 1 and plus 1 just becomes 0. So the x's cancel each other out. So we just have the limit as x approaches infinity, 6 divided by 4, where we know the limit of a constant is just a constant. So the limit of 6 divided by 4 is just 6 divided by 4, or we can simplify it to 3/2. All right, any questions on that one? Right. Okay, so let's say if we wanted to find the limit as x approaches 0 of e to the power of x minus 1 divided by x squared. Okay, so if we take the limit as x approaches 0, e to the power of x minus 1 divided by x squared, and we're going to go ahead and use direct substitution and replace x with 0. Okay, so we have e to the power of 0 minus 0 minus 1 all over 0 squared. Okay, well, e to the power of 0 is 1. So 1 minus 1 is 0 over 0. Okay, so again, we have our indeterminate form. So that means we can use L'Hopital's rule. That means we can take the limit as x approaches 0 of the derivative of e to the power of x minus 1 divided by the derivative of x squared. okay, which is equal to the limit as x approaches 0 of the derivative of e to the power of x is just e to the power of x minus the derivative of x, which is just 1, minus the derivative of -1, which is just the derivative of 1, which is 0, so that one disappears, divided by the derivative of x squared, which is 2x. Which means we apply our direct substitution again. So if we plug in 0, we end up with e to the power of 0 minus 1. So 1 minus 1 gives us 0, divided by 2 times 0, which is 0. So this gives us another indeterminate form, which means we can use L'Hopital's rule again. But this time we're going to use it on this one. So we have the limit as x approaches 0 of e to the power of x minus 1. Bring that minus 1 down. There we go. Divided by 2x. So we know that is equal to the limit as x approaches 0 of the derivative. And bring that up a little bit. I'm trying to avoid running it into this, so I'll just draw a line, make it a little bit easier. You take the derivative of e to the power of x minus 1 divided by the derivative of 2x. That's going to equal the limit as x approaches 0 of the derivative of e to the power of x minus 1 is just e to the power of x divided by the derivative of 2x is just 2. Okay. So again, after we apply L'Hopital's rule, we try direct substitution again. Which gives us e to the power of 0 over 2, which is equal to 1/2. Okay, so we know that the limit of e to the power of x minus 1 over x squared is just 1/2. Yep, sometimes you do have to use L'Hopital's rule 2, 3, sometimes 4 times, depending on the problem. So it's quick, but it can get a little bit tedious doing it over and over and over. All right, any questions on that one? All right. Okay. So we know that it has to be in an indeterminate form to use L'Hopital's rule. Remember that the limit has to be in an indeterminate form. to use L'Hopital's rule, which means it has to be 0 over 0 or some combination of positive or negative infinity divided by positive or negative infinity. Okay, so all that means is that if you have limits and you use direct substitution, and you end up with, let's say, limits that equal 0 times infinity, or infinity minus infinity, or let's say even plus or minus infinity, because both of them could result in it, or 0 to the power of 0, or infinity times infinity. Okay. So if you have limits that equal any of those, you just have to convert them to an indeterminate form. Will have to be converted to an indeterminate form I'll say to use, say before using L'Hopital's rule. Before using L'Hopital's rule. And that's probably one of the most overlooked conditions, is that it has to be in that indeterminate form. Excuse me. Okay, so what if we have the example, say you have the limit as x approaches infinity of e to the power of negative x times the square root of x. Okay. So we could rewrite this as the limit as x approaches infinity. Instead of e to the power of negative x, we can write that as 1 over e to the power of x times the square root of x. Okay, well, if we take the limit of a constant divided by a number getting bigger and bigger and bigger, that limit is just going to be 0. Times the square root of a number that's getting bigger and bigger and bigger, well, that square root will still get bigger and bigger and bigger. So 0 times infinity. Okay. Now, this is not in an indeterminate form. Which means we can't use L'Hopital's rule. Yet. Once we convert it, we'll be able to use it, but we can't use it as long as it's in this form. And sometimes just a little quick change is all you have to do. So as x approaches infinity of 1 over e to the power of x times square root of x, you can rewrite that, just becomes the limit as x approaches infinity. Just move your square root of x right up there. Square root of x divided by e to the power of x. Okay, so now if you take the limit of of your numerator as x approaches infinity, well, that's just infinity. And e to the power of a number getting bigger and bigger and bigger just approaches infinity itself. Okay, so just that one little change, put it in the form that we need. So this is our indeterminate form, which means we can use L'Hopital's rule. So that means that this form here is equal to the limit as x approaches infinity of the derivative of square root of x divided by the derivative of e to the power of x. Okay, so if we change square root of x to x to the power of 1/2, we have the limit as x approaches infinity of the derivative of x squared, of x, is x to the 1/2 power. So we bring down the 1/2 times x to the 1/2 minus 1, which is negative 1/2. Divided by the derivative of e to the power of x is just e to the power of x. Okay, so that gives us the limit as x approaches infinity. That 1/2, if you want, you can factor that out to the front, or you can leave it up there, completely up to you. But that's 1 over x to the negative 1/2 power. Let's just move that to the denominator and make it square root of x divided by e to the power of x. And you can leave it like this, or you can make it 1 over e to the power of x times square root of x. Either way, you'll get the same answer. If you take 1 divided by a number getting bigger and bigger and bigger, that's just eventually going to approach 0, divided by the limit of e to the power of a number getting bigger and bigger and bigger. And that's growing, so we know that actually we can just take the limit of the whole thing just to simplify it. Here the limit as x approaches infinity of 1 over e to the power of x times square root of x. So now we have a number or a constant divided by a number getting infinitely bigger. So we know that limit is always going to be 0. It was just a little easier to do it in this form than that one. All right, any questions on that one? Okay. So let's say, for example, if we wanted to find the limit as x approaches 0 from the right of 2 divided by tangent of x minus 7 over x squared. Okay, so if we take the limit as x approaches 0 from the right, 2 divided by tangent of x minus 7 over x squared. We see that if we have, let's take a quick look at the graph of tangent. We know it has vertical asymptotes at negative pi over 2 and pi over 2. And the graph kind of looks like that. Okay, so we see as x approaches 0 from the right, the value of x is getting smaller and smaller and smaller and smaller and smaller, which means that if you have a constant divided by a number getting smaller and smaller and smaller and smaller, that entire thing is just getting bigger and bigger and bigger and bigger and bigger. So we know the limit of 2 divided by tangent of x as x is getting smaller and smaller and smaller. Well, should have been from this way, from the right, I don't know, but same thing. We know that is just going to be infinity. Okay, minus the limit of a constant divided by a number getting smaller and smaller and smaller and smaller. It's just going to be infinity. Okay, so we can see that this limit is not in an indeterminate form. So we can't use L'Hopital's rule yet. Okay, so what we can do is we can take that limit as x approaches 0 from the right of 2 divided by tangent of x, and we can multiply it by the other denominator. So multiply this by x squared over x squared. Minus that's 7 over x squared. We just multiply that by the first denominator. So tangent of x divided by tangent of x. And most of the time this works whenever you get your infinity minus infinity. If you have the limit of two quotients, or the limit of the difference of two quotients. Okay, so if we take the limit as x approaches 0 from the right of 2 times x squared, so we have 2x squared minus 7 times tangent of x divided by x squared times tangent of x. We just use direct substitution. We have 0 minus 0 divided by 0, or just 0 over 0. Okay, so we can see here we finally have our indeterminate form. Which means we can use L'Hopital's rule. So that means this will equal the limit as x approaches 0 from the right of the derivative of 2x squared minus 7 times tangent of x divided by the derivative of x squared times tangent of x. Okay, so we have the limit as x approaches 0 from the right of the derivative of 2x squared, which is 4x, minus 7 times the derivative of tangent of x, which is 7 times secant squared of x, divided by the derivative of x squared times tangent of x. Okay, so we're trying to find the derivative of two functions being multiplied, so we know we have to use the product rule. So you have the first function, x squared, times the derivative of the second, so x squared times secant squared of x, plus the second function times the derivative of the first, so that's 2x times tangent of x. Okay, so if we did the direct substitution, we'd end up with 0 over 0 again, and we don't want to, not 0 over 0. And let me double check. Nope, we'd end up with infinity over infinity. So we'd end up with another indeterminate form, but trying to find this derivative would just be a whole lot of work. So here we'll try to kind of figure it out. So if we take our limit of 4x minus 7 times secant squared, the derivative of 4x as x approaches 0 from the right is just going to be 0. Minus the derivative of secant squared 0. Well, we know that is just, we can figure that out. So if we have secant squared of x, that's just 1 over cosine squared. So secant squared of 0 is just 1 over cosine squared of 0. Well, cosine squared is 1. Well, cosine of 0 is 1, so 1 squared is just 1. So we know that secant squared of 0 is just 1 over 1, or just 1. So you have 7 times 1, which is 7. Divided by, we know with secant squared, you have a number that's getting almost infinitely small. So it's getting smaller and smaller and smaller, plus a number that's getting smaller and smaller and smaller. So you just add two almost infinitely small numbers together, you get a number that is almost infinitely small sum. Okay. But it will be a positive value because you're approaching 0 from the right. Okay. So if you have a negative 7 divided by this number that's getting infinitely smaller and smaller and smaller, that whole thing is just going to keep getting bigger and bigger and bigger and bigger. So negative divided by positive is always going to give you that negative infinity. So yes, we'll have some to where once you see that that L'Hopital's rule is going to take you down a math rabbit hole that will have you solving it. And then that one would have given you the same indeterminate form, and it would have just been going over and over. All you have to do is say, okay, if I can simplify the numerator and kind of use a little bit of what I've learned so far, you can figure it out without having to apply L'Hopital's rule 5, 6, 7 times. I mean, you can, and you'll get the right answer, but it will just take a very long time. And you'll just get different combinations of tangent and secant squared and all of that. All right, any questions on that one? All right, anyone still writing? Okay, so let's say, for example, if we wanted to evaluate the limit as x approaches 0 of 13 times e to the power of 5x minus 13 divided by 8 times sine of 2x. Okay, so we know our limit as x approaches 0, 13 times e to the power of 5x minus 13 divided by 8 times sine of 2x. If we use direct substitution, that's going to give us 13 times e to the power of 5 times 0, so 13 times e to the power of 0, minus 13 over 8 times sine of 2 times 0, which is 0. So we know e to the power of 0 is just equal to 1. Let me clean that up a little. So we have 13 minus 13, which is 0, divided by sine of 0 is 0. So that gives us 0 over 0. So again, that's in our indeterminate form, which means we can use L'Hopital's rule. So that means this is also equal to the limit as x approaches 0 of the derivative of e to the power of 5x. Uh-oh, got my 13. 13 e to the power of 5x. Minus 13 divided by the derivative of 8 times sine of 2x. Okay, so now we have the limit as x approaches 0. And the derivative of e to the power of 5x is 5 times e to the power of 5x. So we have 13 times 5 times e to the power of 5x minus the derivative of 13, which is 0, so that disappears, divided by the derivative of 8 times sine of 2x is 8 times the derivative of sine is cosine times the derivative of what's inside. So that's just 2 times cosine of 2x. Okay, so we go ahead and multiply those two together and multiply those two together. We get our limit as x approaches 0 of 65 e to the power of 5x divided by 16 times cosine of 2x. Okay, so now we try our direct substitution again. So it's always going to be that cycle of direct substitution. If we get the indeterminate form, L'Hopital's rule, direct substitution. We get an indeterminate form again, do L'Hopital's rule again, the indirect substitution again, all the way until it works. So here, if we use direct substitution, we end up with 65 times e to the power of 0, and e to the power of 5 times 0, divided by 16 times cosine of 2 times 0. We just cosine of 0, but I'll just write out the whole thing. Okay, so e to the power of 5 times 0 is just e to the power of 0, which is 1. So we have 65 times 1 divided by 16 times cosine of 0. Well, cosine of 0 is 1, so it's 16 times 1. So we have the limit of 65/16. All right, any questions on that one? All right. Okay, so let's say if we wanted to evaluate the limit as x approaches 0 from the right of -10 divided by x plus 2 divided by sine of 5x. So if we take our limit as x approaches 0 from the right of -10 divided by x plus 2 divided by sine of 5x, we take the limit of a constant divided by a number that's getting smaller and smaller and smaller. Since it's a negative constant divided by a positive infinitely, well, almost infinitely small value, that's going to be negative infinity. Plus, again, as sine gets closer and closer and closer to 0, this value just gets bigger and bigger and bigger and bigger and bigger. So it's negative infinity plus infinity, or you can put it as infinity minus infinity. Doesn't matter. But we do know that this limit is not in an indeterminate form, which means we can't use L'Hopital's rule yet. So again, whenever you have a sum or difference of two infinite values, most of the time it helps to just multiply by the opposite denominator. We have negative 10 over x. And we're going to multiply that by sine of 5x divided by sine of 5x. Plus 2 divided by sine of 5x. We're going to multiply that one by x over x. So that gives us the limit as x approaches 0 from the right of negative 10 times sine of 5x plus 2x divided by x times sine of 5x. Okay, so now we plug in using direct substitution. Sine of 0 is 0, so that's 0 plus 0, which is 0, over 0 times 0, which is still 0. Okay, which means we finally have our indeterminate form, which means we can use L'Hopital's rule. So we have the limit as x approaches 0 from the right of the derivative of negative 10 times sine of 5x plus 2x. So let me put another bracket just so it matches up. Divided by the derivative of x times sine of 5x. Okay, so that gives us the limit as x approaches 0 from the right. The derivative of sine of 5x is cosine of 5x times the derivative of 5x, which is 5 cosine of 5x. So we have negative 10 times 5 times cosine of 5x plus the derivative of 2x is just 2 divided by the derivative of x times sine of 5x. So we have the first function times the derivative of the second. So that's x times 5 times cosine of 5x. So it's 5x cosine of 5x plus the second function times the derivative of the first. So that's sine of 5x times 1, which is just sine of 5x. Okay. So again, if we did direct substitution again, we'd end up with a constant divided by a number getting smaller and smaller and smaller and smaller. But we don't have to. Actually, we could do it again because we'd end up with -8 over 0. But since we're just approaching 0 and it's not equaling 0, we can't use direct substitution. So now we just have -10 times 5 times cosine of 5. Well, 5 times 0, which is just 0. So make that 5 a little bit neater. So cosine of 0 is 1, so that's just -10 times 5 plus 2 divided by, since we're approaching sine of 0 from the right, that just becomes 0. Or it gets really, really, really small. And this one just gets really, really, really small. It just gets smaller and smaller and smaller because you're multiplying it by a number that's getting almost infinitely small. So you have an almost infinitely small number times an almost infinitely small, well, not times, but plus an almost infinitely small number. You're just going to have a constant divided by a number getting smaller and smaller and smaller and smaller. Okay. Infinitely, oh, almost infinitely, because it can't be infinite. At best, it can be almost or approaching infinity, but it can't be infinite. Infinitely small value that is getting smaller. Okay, so whenever you have a constant divided by a number getting smaller and smaller and smaller and smaller and smaller and steadily getting smaller by the second, and we know that that's going to be, since this is -50 plus 2, we know that's going to be a negative number divided by a number getting smaller and smaller, but it's positive. So it's going to be negative infinity. And sometimes it may help to just graph these two and just say, okay, if I graph, or you can just create a table depending on the calculator you have, and you can just plug that expression in and just see different values of x. And see, as it gets closer and closer to 0, it just keeps getting smaller and smaller. Or if you plug the whole thing in and look at the graph, you'll notice that it's just getting closer and closer to negative infinity, so it will end up looking like that as it gets closer to 0 from the right. So there are multiple ways you can approach it from this point, but kind of working it out this way is probably the, I won't say easiest, but probably the quickest. So as long as you know the concept behind your limits, you should be okay. And if you don't, feel free to ask questions after class. All right, any questions on that one? Excuse me. All right. Okay, so let's say, for example, we want to find the limit as x approaches 0 from the right of sine of x to the power of x. Okay, so if we take the limit as x approaches 0 from the right of sine of x to the power of x, and we use direct substitution, we have sine of 0 to the power of 0. which is 0 to the power of 0. Okay, so we can see here, of course, this is not in an indeterminate form. So we can't use L'Hopital's rule yet. So we can rewrite this as y is equal to the limit as x approaches 0 from the right of sine of x to the power of x. Okay. So this process should look a little familiar because we did kind of the same thing with logarithmic functions. So what we're going to do is we're going to apply natural log to both sides. So we have pretty much the exact same step. So we're applying that to this problem. So that gives us the natural log of y is equal to the natural log of the limit as x approaches 0 from the right of sine of x to the power of x. Okay. So we know if it's continuous, then the limit and natural log, you can just switch those around. Same way you can have the limit of a square root. So we have the limit of the square root of x as x approaches, let's say 2. You could rewrite that as the square root of the limit of x as x approaches 2 and get the exact same answer. Here we're doing the same thing. You have the natural log of a limit. If it's continuous, you can take the limit of a natural log. So you have the natural log of y is equal to the limit as x approaches 0 from the right, our natural log of sine of x to the power of x. Okay, so we know here, now we can apply the power rule for natural logs, or just logarithms in general. Which means we can get that exponent and bring it right down to the front. So that natural log of y is equal to the limit as x approaches 0 from the right of x times the natural log of sine x. Okay, so here we have 0 times the natural log of 0, which still would not put us in an indeterminate form, but we can always rewrite this. And sometimes this little shortcut may come in handy. X is just equal to 1 divided by 1 over x. Because if you multiply the numerator this by x over x, it cancels out at the bottom and just leaves you with x. So we have the natural log of y is equal to the limit as x approaches 0 from the right of 1 divided by 1 over x times the natural log of sine of x. We can just take this natural log and we can move it right up to the numerator. So you have the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of sine of x divided by 1 over x. Okay, well, we know that's equal to 1 in our denominator. 1 divided by a number getting smaller and smaller and smaller just approaches infinity. And with this one, I just ended up graphing it because I had no idea how to visualize what natural log of sine of x actually looked like. So once I graphed it, I realized that it was approaching 0. It was just getting bigger and bigger and bigger. Okay, so we can see here, finally, it's in our indeterminate form. So we could use L'Hopital's rule. So we could rewrite this as natural log of y is equal to the limit as x approaches 0 from the right of the derivative, straighten that up a little bit, of the natural log of sine of x divided by the derivative, and instead of 1 over x, I'm going to rewrite that as x to the power of negative 1. Okay, well, we know that the derivative of the natural log of any function g of x is equal to g prime of x over g of x. And the derivative of x to the power of negative 1 is just negative 1 over x squared. So that will give us the natural log of y is equal to the limit as x approaches 0 from the right, the natural log of sine of x. Since sine of x is your g of x, your g prime of x would be cosine of x. So we have cosine of x divided by sine of x divided by negative 1 over x squared. And just to simplify this one, we're going to multiply it by x squared over x squared, just to simplify that denominator. Okay, so that will give us the natural log of y is equal to the limit as x approaches 0 from the right of cosine of x divided by sine of x times x squared. Oops, bring that up a little bit. There we go. And we'll finish this on the next page. All right, write down where we left off. And that was that the natural log of y is equal to the limit as x approaches 0 from the right, cosine of x divided by sine of x times x squared. Okay. Well, like cosine of x divided by sine of x, we can actually simplify that a little bit. Because we know that cosine of x divided by sine of x, that's just cotangent of x. And cotangent of x is just the reciprocal of tangent of x. So I got my negative. Almost forgot that negative down there. I knew something didn't look right. There we go. So it should be negative x squared. Or the negative, we can bring it out to the front, doesn't matter. So we have the natural log of y is equal to the limit as x approaches 0 from the right of negative x squared times 1 over tangent of x. So we can make that negative x squared divided by tangent of x. Well, if you use direct substitution, you'd end up with 0 over 0, which once again is an indeterminate form. Which means we can use L'Hopital's rule again. Oops. Move that up a little bit. There we go. So that means our natural log of y is equal to the limit as x approaches 0 from the right of the derivative of negative x squared divided by the derivative of tangent of x. Which means that our natural log of y is equal to the limit as x approaches 0 from the right. The derivative of negative x squared is negative 2x divided by the derivative of tangent of x is secant squared of x. So if we use direct substitution again, we have the limit of 0, which is 0. And the limit of secant squared of 0, well, secant squared of 0 is just 1. So 0 divided by any non-zero number is just 0. So that means that our natural log of y is equal to 0. Oh, move that one out the way. Okay, which means we're really close to our answer, but we're looking for the value of y, not the natural log of y. Which means we have to raise both sides to e. Because remember that e to the natural log of the power of natural log of y is just equal to y. So if we take e to the power of natural log of y, that's equal to e to the power of 0. I really didn't need the parentheses around that. Don't know why I put them there. So again, the e and the natural log, they cancel each other out, and we're left with just y is equal to e to the power of 0, which is just 1. So we know that the limit as x approaches 0 from the right of sine of x to the power of x is equal to 1. So we did all that work to end up with 1. All right, so any questions on that one? Okay. And again, this process should look a little bit familiar from the derivatives of logarithms section. The only difference is we added a L'Hopital's rule to the process, but the steps themselves are exactly the same. All right, any questions? All right, so we will go ahead and stop there. We will start on 410 tomorrow. Then after we're done with 410, I'll post the exam. And I'll probably end the class after 410 because you have the chapter 4 test. So if you have any questions on anything in chapter 4, of course, feel free to stay back and ask away tomorrow or today if you have questions. But if not, I will see you tomorrow. Remember to start 410. All right, you too. Thank you. Hello.
I wanted to ask about when you had the limit of log of sine of x, you could just swap the limit and the log. You said you could also do the square roots.
Yes.
I don't understand that, and I feel like I should if I'm.
Not a problem. Yep, it was a while ago when we went over that, so no problem at all. So if you have, let's say if you wanted to have the limit, as, let's say as x approaches any number, let's say x approaches 5, of the square root of x. You can just use direct substitution if you wanted to and make that just the square root of 5, or you could rewrite it as the square root of the limit of x.
Right, because the limit of x as x approaches 5 is just 5.
Yep, so all of that just turns to 5, so it's still going to be the square root of 5. So it's the same thing with the natural
same
logs.
principle with the logs. Okay, cool, thank you.
You're welcome. All right, have a good hello.
Sorry, I was panicking yesterday a little bit.
Oh, okay, yeah.
But so if it doesn't work on my computer, would I be able to borrow one?
Yep, you can borrow one, or you can use the computer lab here.
Okay.
Yep. So if you go to the like the Student Success Center or Testing Center, they have computers there you can use, and they're all compatible with Respondus.
Yeah, I'll probably have to do that because I tried it on 3 different computers.
Yeah.
So
If any MacBook or Chromebook,
yeah.
they are glitchy as all get go on all of them.
Yeah, I'll probably have to figure that out. But hopefully I'll be able to take the exam this week.
Okay.
Thank you for your help.
You're welcome. So start 14 on Wednesday.